Afternoon, everyone. Let's start the session. Okay, so we are in the module 3. So in before Cat 1, we have learned about this electrostatics and magnetostatics, and we have moved to electrodynamics. So electrodynamics is dealing with time varying fields. So by applying the time varying potentials between the plates or between the uh, between the coils, we can achieve the time varying electric and magnetic field could be possible. And this time varying electric and magnetic fields almost ruling the world in terms of the electromagnetic radiations, which are useful for wireless communication and in many heating applications, in many radar applications, and in vehicle, motor, everywhere actually this time varying fields are used. And in order to design such systems, we need to understand the behavior of this time varying fields. For that reason only, we are studying two important concepts. One is Faraday's law, another one is Maxwell's equations. So in Maxwell's equation, we have summarized all the important laws like Gauss law and Ampere's law and Faraday's law. And also we have seen that the Gauss law of magnetostatics. So these four important equations we have derived. Also, we have seen one of the very important concept, that is displacement current, and this displacement current is the reason for the radiation from any particular structure. So this displacement current is the starting point of the antenna theory, and therefore it led to wireless communication. So almost all the wireless communication systems will be having antennas, and therefore uh, the antenna design is very unique field. So how to exert the displacement current from a particular structure, that is all about the antenna theory. These are all the things we have learned so far. Now we are actually going towards the same, the time varying fields or the electrostatic fields, whatever the fields, how they behave in a conductor or dielectric material, or in general in a medium, how they behave. So that is what we are going to study. And whatever these all aspects, these all we are going to discuss with the classical electrodynamics. So this classic electrodynamics, there won't be any structure of atom or anything else. So this all tells about that this material is almost uniform, and these all made up of molecules, and these molecules are uniformly arranged. Like that means only they have studied. So this classic is, we can classify that it is before the year uh, the beginning of the 20th century. So after that only this quantum mechanics, all the quantum mechanics concepts evolved, and there actually they have started to clearly define electron, proton, and all the subatomic particles. And there comes band theory, all these things. So the band theory will not come here. Anyhow, this classical mechanics is sufficient enough to describe the very important properties. So these classical mechanics often referred in the physics as bulk. So bulk in the sense, everywhere we are going to consider almost uniform behavior over the space or a given volume structure. So this is what you have to keep in mind when you study this particular concept. So in case of the materials, um, the electric field and magnetic field, so far now what we have seen is this actually traveling in a empty space, so where nothing is there. So we generally use two quantities. One is epsilon naught and mu naught. So this is actually vacuum permittivity, and this is vacuum permeability, and these values are highly depends on the uh, how this electric and magnetic field are distributed over the structure. And so that is often referred as vacuum electrostatics. It's also very useful. For example, when you go outside the earth, obviously it is vacuum electrostatics only you will study. And there is huge advantages there in uh, while uh, while you go outside the while you go outside the space, at least in terms of electronics. Okay. So in case of the materials which are actually defined, so they will be relevant or relative to the vacuum electronics, and that is comes with new properties like the relative dielectric constant and the relative permeability. All these is going to come. And these materials in the electric or magnetic fields, they will be divided into two important materials. One is conductor, another one is dielectric. And later, after the understanding of the magnetic fields through electron spin, they have further divided this dielectrics into uh, dielectrics and the magnetic materials. So this dielectric material and magnetic material, they will be having completely different behavior. So this magnetic material is, it is because of the electron spin in the outermost orbit. So in the outermost orbit of the atom, we have uh, valency electrons. These valency electrons normally will be having one particular spin. So due to, with respect to the spin, we will be having this magnetic field. And similarly, another spin will be there. This another spin is going to give another magnetic field. So normally in a dielectric material, both the spin will be available. They cancel each other. Therefore, there is no overall magnetic field. But in some materials like iron or alloy of ions, you will see that any one of the uh, electron will be missing. Therefore, one particular uh, electron spin become dominant, and that induce the magnetic field. So, but in the classical electrodynamics or classical field theory, we have only two structures. One is conductor and dielectrics. And in fact, it is more than sufficient to define at least 90% of the structures. So that is why this theory is still successful. In fact, till date, actually, many people are using simple electromagnetic field theory to solve even hard problems. In this two structures like conductor as well as the dielectric material, the flow of electrons will be there. This flow of electron, which we call as the current, and this current, uh, which defined as the movement of charge carrier with respect to time. And further, we define this in terms of the current density over the given space itself. And this current divided into three currents. One is conduction current, another one is convection current, and the displacement current. So the conduction current is nothing but the current which is traveling in a conductor, and convection current is nothing but the current traveling in non-conducting structures like dielectrics materials and semiconductors or magnetic materials. So in that, how the current is flowing. And all the third one is displacement current. For this displacement currents, there is no material or any other space is not at all required. They can simply go outside the structure and they can travel in any direction. And there comes the radiation. Okay. And the displacement current we already studied. This convection current we will study in the next unit. And today we are going to see about this conduction current. So this conduction current, as I already mentioned, this is actually characterized as the flow of charge carriers in a conductor. Conductor means simply understood as the sigma is very high value. That means the conductivity is very high. And if the conductivity is assumed as infinite, then this conductor is often referred as perfect conductors. And these conductors or perfect conductors, whenever we consider, and directly the metals will be coming into the pictures. And it is because the metal has huge amount of electron within the free electrons. Okay, so these free electrons need very little force to be applied in order to move. So uh, unlike the other material space like other semiconductors or other insulators, you need to give very high electric field across the material to make it flow. So the force which is acting on a particular electron can easily be described as, the force is nothing but the Q into the electric field what is required. Okay, so this is the electric field which is available inside the material, the conductor. And so this, let's say we have this anode and cathode. This is a metal and huge amount of electrons are available. The moment you give the voltage across this anode and cathode, the electric field will form, and this electric field will allow make the charge flow, and in the opposite direction. So the forward direction we call the conventional current, and the opposite direction, which is a real current, which we call electron current. And this is the force required for that. And this force we can easily calculate with respect to the movement of charges. So we know that F equal to ma, and m is the mass of the electron and a is the acceleration. This acceleration can be easily calculated as the drift velocity and the mean free path time. The mean free path time is nothing but the electron will not travel in a metal simply by like straight line. It will take a zigzag path. So two uh, between two uh, mm, collisions, we have a time that is we call mean collision time or mean free path time. So this mean free path time, if we know that, then we can easily calculate the acceleration. So by this, we can easily equate with this minus E. So by the way, you can easily calculate the drift velocity. Once you calculated the drift velocity, it is very easy to calculate the total current density, because we already know that this uh, the current is nothing but moment of charge carriers, and simply have to equate with the uh, electric field itself. So that is what is going to give the drift velocity. And when you multiply with this the number of charge carriers, then you can easily get the current density will come, and there comes the current. Sorry, the conductivity will come, and there comes the current. So current density is nothing but charge density into the drift velocity. And when you substitute this equation in this, then you will get the equation this, where sigma is nothing but uh, n into e square. So this e square tau by is nothing but already it is mobility, and there comes the conductivity, and you will get this expression. And this is the expression originally known as Ohm's law. And later we have this conductivity is nothing but 1 by rho. And when you substitute this, you will get electric field is nothing but rho into J will come, which is nothing but V equal to R into I. That is nothing but the Ohm's law. Okay. So this is this J equal to this is nothing but the conduction current, and this is by applying the voltage across any particular terminal of a metal, then the force is induced, and due to this force, the current density. So this force is highly depends on the mobility of the electron within the metal structure. As this atomic size increases, then the electron collision rate also will keep on increase. And for example, for iron, and then for big this tin, antimony, all these materials, you will be having less conductivity rather than uh, high conductivity. So that is why they are actually often referred as quasi metals or quasi conductors. So some of the materials, some of the metals, they are showing naturally resistive nature. So they can be utilized for controlling the currents. So in fact, many resistors are made up of tin or tin oxide or antimony, like that materials. Okay, so how this the field is responsible for the current flow, and how this field will be available inside a conductor. Assume that there is a metal is available, a rectangular metal plate is available, or a metal structure is there. So this is the metallic structure, and a field is actually traveling along the side. Okay, when the field is actually crossing this, when it is trying to cross this metal plate, what will happen is the external electric field. Okay, and which will induce a internal electric field. So we know that the electric field travels from high potential to low potential, like plus to minus it is moving. So obviously this electric field will make a negative force that makes the electron to move to the one particular surface. So the electrons will be this side and the positive charges will be in the other side. In fact, uh, then it actually divides this into two, and this internal electric field is separating the charge such that actually this electric field is equal to this. So you will get the external electric field is equal to the internal electric field induced by the displacement of the charge carriers. And since both are equal, the electric field, the total electric field inside the metal is always zero. So in other words, the electric field cannot pass this material. So what will happen? This is, let's say, here I am taking a cross section view. This is the metal. We have a thickness of a particular metal. When the electric field travels and it cannot penetrate because already electric field equal to zero and it cannot penetrate. So thereby it's supposed to reflect back. So that is what the only way the law of conservation also can be obtained. So all the currents whichever is all the electric field whichever is coming and hitting the metal plate will be reflected back. And what about the other directions? And it will be reflected in the, so it looked like a mirror for a electric field. So this is the general perception of the electric field whenever the electric field is coming outside the conductor. When the electric field is induced inside that, then we will get the moment of charge carriers due to this conduction current. And in that case, since the electric field inside the metal is equal to zero, then we know that the electric field is always due to the potential. So everywhere else actually you can find that the potential at any particular point in the conductor is always be uniform. So if you take the point A and if you take the point B, then always the potential at A and B will be equal, and that makes the potential everywhere equal, and that is often referred as equipotential surface. So this equipotential surface, if it is completely uniform means like like it is a very uniform surface, there is no bends or anything else, then everywhere you got the same potential, and such a surface uniform surface potential is often referred as equipotential surface. And so that is the general structure always assumed as ground. And this generally makes, this is another one behavior of a perfect conductor with sigma is equal to infinite. Okay. So this is how the metals or the any particular structure will not allow the electric field inside. So this is why whenever you go in a elevator, obviously the mobile phone will not receive signal or signal will be received with very low level. And this is all because of the the metals which are having the properties of the conductors. But what about the electric field if it is applied on the conductor itself? So we are taking a conductor, and in this conductor we are actually having two conducting planes with anode and cathode, and this anode is connected with positive, the cathode is into negative of the power supply, where we are actually going to give a potential of P. Therefore, there will be a current will start to flow, and this charge flow, which is a conventional current, and for electron it is opposite current, and that makes the electric field inside. This electric field is not equal to zero, obviously, and that makes the overall flow of charge. So this electric field we can easily calculate. It is nothing but V by L, where V is the potential and L is the length of the conductor what we choose. And this creates the electric field, and this electric field will be responsible for the force. And this force we can calculate as Q into the electric field, and this force will make the electron move, and that is responsible for the conductivity. And in order to define this conductivity, we often use the resistivity as the one. So we have the resistivity, which is nothing but 1 by conductivity. And this resistivity, if you multiply with area of the conductor and the length of the divided by area. So if you multiply the length and divide by area, then you will get the resistance. And that is why the Ohm's law, what we refer in field theory, has converted into in terms of R, and you got this V equal to I into R, and which is famously known as Ohm's law. But this is actually very late, like in the 20th century itself, it's been called often often treated with Kirchhoff's law, because Kirchhoff only has described the almost the very first one after Ampere. He is the one, he explained about the current flow in a metal or in any other material, how it works. And in fact, in this very same year itself, Maxwell parallelly works in field theory. So that particular period, at least from 1830 to 1890, this is like one of the golden period for field theory. And 1824, Ampere described the Ampere's law, and many other important law, including Gauss law. All these things have been very first time derived. This actually Ohm's law, which is describing the resistive nature of a particular metal or a particular dielectric material, and that is described by the conductivity of it. So as the conductivity is high, the resistivity will be low, and that allows the current. So this is one of the important properties of that. And the question is like, can we get this resistance negative is possible or not? So what about anybody has any idea that whether the resistance can be negative?
No, sir, resistance can't be negative.
Okay, so we know that resistance is nothing but V by I. So if you put a negative voltage, then we will get negative resistance, is it?
So negative voltage will give us the negative current, which will cancel out and will get a positive resistance value.
Great, that's correct. Yeah, but we can achieve this negative resistance or negative differential resistance by means of one interesting property. So if you have a device with four IV characteristics in this way, and this is positive resistance, okay, where the di by dV is positive. But here, if you see that this is actually di by dV is negative. So this way we can get the resistance negative. So if then resistance is negative, there are some interesting behaviors will come. Like one can easily generate oscillations, microwave oscillations with this negative resistance. You will study these things in the microengineering concept. It is one of the very interesting concepts. And now very recently, people are working on one-port amplifiers. So this one-port amplifier will be having only one port, but it will work as very similar to that of the amplifier with less biasing issues. So I think in the near future, this one-port amplifier will pick up, and which is mentioned in one of the which we call white papers. White papers means the industry itself will say that this future technology is going to evolve like that. So you can find it in the HP, that is a Keysight website itself. Keysight is nothing but one of the important company out of HP for very high frequency measurements. Okay, so far now we discussed about this conductors. And the next possible dielectric material is dielectrics. So the dielectrics, the name itself, it is describing something comes with die, and that is nothing but dipole. So if you take any particular material which is made up of molecule in the sense it can be H2 or H2O like that, and many of the such hybrid systems like H2O or this indium phosphide like that. Whenever we have this kind of material, then there will be material will be always be oriented in a particular way. And the moment you give electric field, let's say you are giving electric field in this direction, then these charges, let's say the hydrogen and oxygen which are sharing the charges, here also 2 plus charges and another 2 plus charges, and the remaining uh, charges nearly around 6. So totally about 10 electrons will be available in one particular side. Okay, this is actually this plus minus like that. So towards the plus it will be going, and this side actually it is more like the absence of electron, which looks like plus. So this immediately will make, instead of this shape, obviously the water molecule will be elongated in this way, where the two hydrogen atoms will be coming here and positive negative behavior will come. And immediately this positive negative behavior will create the dipole. In fact, cannot be uh, these cannot be uh, separated. Means this always be separated by a distance. So whenever we have positive charge and negative charge separated by a distance, and this distance is very, very small, and it will be in the dimensions of this charges itself, and that is often referred as dipole. And these dipole, even though they are actually made up of two charges, and there is a possibility of that they can cancel each other, but they will be canceling each other within the structure itself. But outside that, it is not so. So in outside, when you measure the electric field at any particular point, you'll be still having the electric field. Okay. So because of that, this dipole again will behave like a single quantity. And in order to define that, we often use uh, a property for this dipole, as that is called dipole moment, which is represented by P, which is nothing. This is plus Q, this is minus Q. So total Q into D. So that is nothing but the dipole moment. So the dipole moment is nothing but the induced electric field due to this dipole itself. And this is the general nature of many molecules. And this classified as uh, dielectrics. So in this dielectrics, we have many materials like insulators, and then we have other semiconductors, and then magnetic materials, and even superconductors. Everything else actually comes in this particular category only. And so the displacement of electron within the molecular structure itself is making the dipole. And this dipoles will be randomly arranged in any particular material. But the moment you give electrodes with positive and negative, then the electric field produces. This electric field will make this, let's say this, when the electric field is now it is means which is randomly oriented. And the moment you give the electric field, then the positive charge will be oriented in this side and the negative charge will be oriented in this side. And therefore, the induced electric field will be in the opposite side, which we refer as the moment. So here you can see that the moment is in different direction. Therefore, the net electric field, the total electric field inside the dielectric material, we can assume it is approximately zero itself because it is randomly distributed. They cancel each other. Obviously, they may become zero. But the moment you give the electric field will pass and will orient everything else almost in the same direction. Therefore, the E total is equal to the electric field which is already available due to the, let's say the electric field is E naught. So I am giving electric field of E naught because of the two parallel plates, and the parallel plates are having the separation about D. So this E naught is nothing but V by D. So this is the external electric field, and there is an internal electric field due to this so-called dipole moment. So you will be having E naught plus EP. There will be two electric fields will come, and this EP further can be defined in terms of E naught. So we have individual dipole moments as Q into D, and if we have n number of dipoles in a given volume or in a given unit volume, then you can simply add all of them. So if all the dipole moments are almost in the same direction, you will get n into QD. So this is the approximate value, and this, if you divide per unit volume, then you will get the net electric field induced by that, which is often referred as polarization. So the polarization is nothing but the electric field which is induced by the dielectric material because of external dielectric field, and it is always most probably will be opposite to the field direction, sometimes in the same direction. It is purely depends on the way the dipole moment is oriented with. And this dipole moment is happening because of the external dielectric field. So this external dielectric field is going to align all the dipoles in a particular direction such that the total or the induced or the electric field inside that both are same. So due to that, the dipole moment is induced. So there is a relationship between them, and that relationship is given by the polarizability. So that is often referred with this chi value. Chi, or this chi will be always be used. Okay. So the polarization, which is the internal electric field induced by the material due to the external electric field, is represented in this form, and this is a proportionality constant, and therefore we can calculate the total electric field. The total electric field is nothing but the external electric field plus the psi E epsilon naught, and this epsilon naught, since the epsilon naught is coming, we have to mention in terms of D. So the total flux density D, total flux density is nothing but the D naught inside plus the D due to the polarization, where P is already given here, which is nothing but this. So this is nothing but epsilon E plus psi E epsilon naught E. So you can take this all the values and you will get 1 plus psi E epsilon naught E, which is nothing but the total. So this is the total flux density which will be available. Surprisingly, since the value add each other, compared to the excited, or so compared to the external electric field, the internal electric field inside the dielectric material will be higher in terms of the polarizability. This polarizability highly depends on how this material is oriented and how flexible this can be moving. Many factors involving in that. So this 1 plus psi is often referred as the relative permeability. And so in case of material science, they will calculate this and we will add this one. And in electrical engineering, we always use this relative permittivity, which is also referred as dielectric constant. So if you say that, let's say some liquid is the water itself, we have H2O and we have two parallel plates. And let's say there are some ions there inside, and which makes this material highly polarized, positive, negative itself. The moment you give the electric field, this will start to orient in the particular direction. So all these dipole moments will add each other. And if there are n number of, I have to write small p, and by having this n number of molecules there, you will get the polarization. And this polarization will give the total electric field, and which is giving the rise to the expression for the dielectric constant. So the dipole mechanism which is available inside the material is giving a parameter for dielectric constant. And in fact, Niels Bohr, when he studied, he actually, in order to study, he thought of taking the simplest material that to be studied. Of course, hydrogen was that, but hydrogen is very difficult to study with. And what he did is he actually studied for water itself. The dipole moment, which is calculated in his time with the best possible accuracy, was this. And from this dipole moment, and we know that there are about four shared charges here, two shared charges, and six unshared charges will be available in the valency orbits, which are then will give the total charge as minus 10 electrons. And if you divide by that, you will get the distance between the total d will come. The d is nothing but the distance between the positive, sorry, this is actually negative, and the positive charge. So this value, you can see that this actually 3.9, which is nothing but 0.039 nanometer, while the hydrogen atom is considered to be about the size of 0.15 nanometer. Therefore, if this is the hydrogen atom and if this is the oxygen atom, and the distance is smaller than the radius of it, so which gives the idea that they supposed to be like this. Other words, the hydrogen atom and the oxygen atom, they almost merge each other. This is one of the very important puzzling behavior which made Niels Bohr to think that this atom is not a solid structure. It is kind of a wavy structure which is flexible one, and they can easily merge, and they produce some new type of bands here. Can anyone say that what that new type of band? Which within the very few year itself, Einstein told about the two bands, the valency band and conduction band. Here is a very simple example. So there is a two parallel plates, and these two parallel plates are separated by a polymer material which has the dielectric constant of 2.55. And these two parallel plates give are connected with the battery such a way that the electric field is 10 kilovolt per meter. Okay. So then the separation distance is given with 1.5. So that is D, which is nothing but 1.5 mm. Now we have to calculate the flux density inside the material and the polarization and the surface charge density, or the total charge density which is available inside the dielectric material, and polarization charges. The polarization charges is the number of dipoles and the potential between this two. So potential is nothing but the total voltage. We have to calculate this total voltage. So we already know that V is nothing but, sorry, the electric field is nothing but V by D. So obviously you can easily calculate V is nothing but electric field into D. Electric field is known, which is nothing but 10 kilo, so 10 power 4 volt per meter into 1.5 millimeter into 10 power. So obviously when you multiply that, you will get 15 volt. And the D is nothing but the total, just a minute. sorry. So this D can be easily calculated, which is nothing but epsilon naught E. Electric field is known, dielectric constant is known, permittivity is well known. So this is the epsilon naught, and the electric field. So when you multiply, you will easily get that. And how to calculate the polarization? So we can easily isolate the polarization from the D by subtracting this epsilon naught E. Otherwise, we can calculate the polarizability. The polarizability is nothing but epsilon or minus 1. So whatever the value, it is 2.55 minus 1, that is 1.55. So polarizability, epsilon naught, and the electric field. So you can easily calculate that. Once this polarization is calculated, then you have to, then it is another D. Okay, it is due to this is the flux density created by the dipoles. And when you simply multiply with the vector, that is vector of the electric field, so the unit vector of the electric field, when you calculate, then you will get the charge density, because we already know that according to Gauss law, this del dot D is nothing but the charge density itself. So the smallest possible one is nothing but the flux density itself. So the flux density is nothing but the polarization. So both the value will be same only. The only difference is it will be having a vector, and that vector is in the direction of the same as that of the electric field itself. And the total charge density can be calculated in terms of the D itself. So this two value will be same, and the V already calculated. So this is a simple example you can work out with. And this materials can be further divided into two. One is polar material and the non-polar material. The polar materials are nothing but the means naturally this dipoles will be built in, and therefore the polarization will be readily available. Many materials are available. For instance, water is already a polar material itself, because it will be naturally aligned and you'll get fields. But since they are randomly placed, the water may not give you the electric field. But the moment you induce that, then it will come. And the non-polar material is nothing but we need to give electric field in order to make the dipoles. And many materials, many solids will be having like that. Most of the metal oxides are non-polar materials. So you have to give electric field. So all these materials like conductors and dielectric materials, they take their properties. Let's say if you take the conductor, it is nothing but the conductivity, and dipole, it is having polarization. All these things, they start to behave when you apply the external electric field. Okay, or external magnetic field, when you apply, they start to behave. And this behavior we are actually calling as the reactance. And in this reactance, we have resistance, capacitance, inductance, all these behaviors will come. Okay, so these properties we will explore in the next class. We will apply the electric field inside the dielectric. If we take a dielectric material and dielectric material, what will happen? If it is a dielectric and metal, metal, dielectric, metal, metal, like that, if we have four different combinations, how this electric field will travel from one to another, and how to calculate the electric fields. And this is very, very important one. And the semiconductor devices, everything else were constructed upon this particular theory only. For instance, if you take the MOSFET, I think all of you know about MOSFET. MOSFET has semiconductor. Upon that, we have oxide and the metal. So the electric field is traveling from metal to oxide, oxide to semiconductor. So this is a conductor, this is a dielectric material, this is a dielectric material. And in order to calculate the electric field which is traveled up to this, and this electric field only makes the charge carriers to move, attract, and makes the depletion layer. I believe all of you know about that. And these all things can be studied with this simple concept that we will see in the next class. If you have any questions, you can ask.